Okay, so now I just okay. Okay, good. So hopefully everybody can see my screen. Yes.
Yes.
Excellent. Right, good. Okay, so I shall get started. First, a little bit of introduction about myself. As you can see, my name is Simon Ritter. I am the Deputy CTO at Azul. I have been working with Java really since the beginning of Java, because I joined Sun Microsystems way back in 1996, about the same time that JDK 1.0 came out. I followed Java all the way through the Sun years, got acquired by Oracle as part of the Sun acquisition. Spent another 5 years at Oracle. We then parted company, and I joined Azul about nearly 7 years ago, which is just scary to think how old I am now. Anyway, what we're going to be talking about today is, as the title says, Java on CRaC. Now, I do have to say that, from a marketing perspective, we might have to have a little bit to think about the naming of this. It's certainly provided some entertainment for us as a company, because we started this project, and of course, people come up with ideas about this, and they say, "Ooh, why don't we have a centralized service to relate to this? And then we can call it the dealer, and then we can have the CRaC dealer." Again, I think we may have to have a bit of a discussion from the marketing department. So, what is Java on CRaC? What are we actually talking about here? Well, the first thing we need to talk about is why Java is so popular. And I think there are a number of reasons that we can see that Java has maintained its popularity over the last 27 odd years. First of those is the basic idea that it's a great language. It's both easy to write and it's easy to read, which is very important, because we know that we spend a lot of time maintaining software, both written by ourselves and other people, as well as writing new code. And I think that the developers of Java, people like Brian Gertz and Mark Reinhold, have been very good at adding new features to the language in a controlled way that has kept the essence of the language, but still added things like Lambda expressions, the Streams API to give us more functional style programming. We've seen things more recently in terms of like pattern matching that have added lots of new interesting things, and even Project Loom that we'll see in JDK 19. It has lots of great libraries, and because we've got 27 years of history, it's a very popular language. I think whenever you start a project, you're going to be looking around and there will be some kind of library or framework that's going to be able to help you with what you're doing. And it'll either be free, open source, or if you want a commercial supported version, that'll be there as well. You just have to think about things like Spring, Spring Boot, Java EE, all of those sorts of libraries, but then extending into, basically anything that you can think of in terms of like machine learning or, vision or anything like that. There's a library for that. The third reason is that we have a great community. The fact that, I'm doing a presentation to a Java user group at the moment is part of that. There are lots and lots of Java user groups around the world. I've been very fortunate to visit lots of them. A few weeks ago, I was in the US and I went to 4 different JUGs. So I did Ohio, I did Nebraska, I did Idaho, and I did Kansas City. So, lots of JUGs all over the place, Java champions, lots of, sort of ideas behind this. But I think the most important thing about why Java has maintained its popularity is the Java virtual machine. And if you go back to the beginning of Java, we had this marketing phrase, write once, run anywhere. You compile your code into bytecodes, and then you don't have to care about whether you're deploying it onto a Windows machine running on Intel, or whether you're deploying it onto a Linux machine running on an ARM processor. Same set of bytecodes will work on any platform. The other thing is there's excellent backwards compatibility. I've literally taken code that was written on JDK 1.2 and compiled on 1.2 and run it on JDK 17 with the JRE, and it will run without any problem. I did find some code that had been compiled with JDK 1.0, but that was only applets, and because applets aren't supported after JDK 11, I couldn't try that, but really excellent backwards compatibility. And the key thing about the JVM itself, which is what we're going to talk about in the rest of the presentation, is the idea of a managed runtime environment. It does a lot of things for the developer, which if you look at languages like C and C++, you have to do manually. So the JVM handles various things for you. Now that doesn't come without a cost. And one of the things we see is the idea of warm-up time for applications. When you start your application, what's happening is we're taking the bytecodes in a class file, and the JVM loads those. And remember that these are the instructions for the Java virtual machine, not a real machine. At some point, those instructions have to be converted into whichever platform we're running on. That write once, run anywhere needs us to take bytecodes and convert them to Intel instructions for Windows or ARM instructions for Linux and so on. Now, how that happens is in a number of different ways. So initially, what we do is we take those bytecodes and we interpret them. And interpreting is where the JVM is taking each bytecode in turn and then converting that bytecode directly into a set of instructions for the platform it's running on. It does that using a set of templates. So when you start up the JVM, it will create a complete set of templates for all the bytecodes in the instruction set for whichever platform it's running on. And that way it can adapt to the microarchitecture of the platform and do various things like that. But there's no chance of optimization in this case. It's literally one bytecode, take the instructions and execute them and do nothing in terms of trying to optimize. Literally the only thing that you'll find when you look at the templates in the JVM are there are a few occasions, literally sort of 3 or 4, where they double up bytecodes because they happen so frequently together and they create a template for that pair. But that's really it. To get around that problem, and that was the reason when Java was first released that it was always criticized as being slow compared to C and C++, what the developers did was they used an existing technology, which is just-in-time compilation. Now, how that works is that the compiler, the virtual machine will keep a track of the methods that are being called, and it will count how many times each method is called. When you get to a certain threshold, the JVM will say, aha, this is a hotspot in terms of our code, hence the name of the JVM. And it will then say, rather than interpreting each bytecode in turn, let's pass that to an internal compiler and generate a set of instructions for that method. That uses what's called the C1 compiler, very innovatively named. And what that will do is very quickly compile the bytecodes into a set of native instructions. It doesn't do a huge amount of optimization. It can do some basic things, like it can do some method inlining, it can do some dead code elimination, but it doesn't really do much beyond that. So it's the idea of getting it compiled quickly, so at least the code will run a bit faster. What then happens is that the code that's being run, generated by the C1 compiler, will also include profiling, and we can collect information about what the code is actually doing as it's being run. When we get to a second threshold, where a method is being used very frequently, and so it's a real hotspot, we then pass it to a different compiler, and that's, again, originally named the C2JIT compiler. What this does is spend longer compiling the code, using the profiling information that's been collected, compile it and optimize it as much as possible based on all that information, plus a very clear picture of what the machine is that we're running. So we know exactly which microarchitecture is in use. We can then optimize based on that, various things like that. So that then gives us a high level of optimization for our code. Now, the problem with this is that's great. And so once you've got to the point where all your frequently used methods are being compiled through C1 and C2, you get a nice high level of performance. If you stop your application and you start it again, everything goes back to the beginning. So we have to go through the same process of analyzing which methods are called frequently, compiling them with C1, profiling them, recompiling them with C2. And that's very inefficient. What it leads to is this idea of warm-up time. So if we look at a typical performance graph for application code running on top of the JVM. This is what we're going to see in terms of the speed of the application. Start off on the left-hand side. We start off slowly because we're interpreting each bytecode in turn. Then we get the green area, which is where we've compiled some C1 code, and we're then running a bit faster, doing some profiling, and then gradually we'll get faster and faster as we compile all those methods using C2, and ultimately you get to this point where all the frequently used methods are compiled and so on. You'll see some dips in performance as we go through that warm-up, and those are as a result of what's called de-optimizations. And I'll come back to what that is a little bit later on, because it's quite important. But as we know, however long it takes to get to this optimum level of performance is the warm-up time. Now, that could be a couple of minutes, it could be a couple of hours, depending on what the application is doing. You could spend literally days warming up your application, depending on how the application is exercised. So again, the problem we face is that if we run our application, we look at this graph and we see the warm-up time, all of the work that's involved. And when we run the application a second time, we have exactly the same profile for the graph, even if it's exactly the same workload. And when we run it a third time, the same thing happens. What we would really like to have is a better approach where we can allow it to run, allow it to warm up, allow it to get to this heavily optimized performance level. But then when we restart, when we restart, we see exactly the same level of performance. So we pick up exactly where we left off, and therefore we get all of the optimizations, all of the performance that we generated when we ran it the first time, and when we run it a third time, then we get the same thing. So this is what we really want to have happen. Now, one of the things that, if you look at ways that Oracle have used to try and improve the startup time of applications, one of them is application class data sharing. And I included a slide in this presentation because this was a question that I got when I did a version of this presentation earlier on. And people were asking me about this and how does that impact on the startup time of applications. So I thought I'd just briefly cover this so that you get an understanding of what can be done to help improve application startup time, but it doesn't solve all of the problems. So application class data sharing, what that says is that when you start your application, the first thing JVM has to do is load the classes that it needs for your application. So your jar files, your class files, and so on. When it loads those classes, it has to do verification of them to ensure that the structure of the bytecodes doesn't break the standard and you're not trying to give it bytecodes that could do something malicious. The JVM will then build some internal data structures that represent those classes and execute your bytecodes. Again, when you start up the next time, it has to do the same process of loading the class files, doing the verification, and doing the building the internal data structures. Application class data sharing says, right, once you've loaded those classes, we'll write out the internal data structures to a file. And when you start the application again, rather than having to go through that whole process, as long as you can verify that the class files haven't changed, then all we do is reload or literally map that file into memory, point the internal data structures at that area of memory, and everything is ready to go. So it does improve the startup performance of applications a little bit, but it doesn't address this whole point of the compilation of code and moving from interpreting to C1 to C2 and so on. So it is a start, but it's not the whole answer.
Hey, Simon, there was a question. There was a question in the chat.
Sure. Oh, hang on, let me look at chat.
Yeah, so
right. Okay. Is there any room to make the interpreter faster or the C1 fly lower? Yes. Okay. You can't make the interpreter faster, really, because interpreting, as I say, just uses a template way of doing things. And the way to get performance out of code is to optimize based on looking at large pieces of code. So you have to look at methods. You can do things like method inlining. You can do things like, as I said, dead code analysis. But then there's a lot more in terms of speculative optimizations, which I'll come to in a little bit. And those are the kind of things you cannot do with interpreting. It just doesn't work that way. C1, again, there is a little bit of possible improvement in performance. We did look at that when we were working on some of the stuff we've been doing. But the thing is that because when you get to the optimized level of code, everything that's running frequently is going to be compiled by C2. Changing the way the interpreter works, changing the way that the C1 compiler works won't have a huge impact on the overall performance. You might be able to squeeze the graph a little bit down to the left, but the amount of work you'd have to do on that just to gain a small amount, you'll never be able to really make a big dent in it. Just doesn't really kind of merit the amount of engineering effort that it would require to do that. So
there's basically no room to make the startup fast. I don't want to have perfect performance up front, or just basically have the startup basically being faster, and the first minutes basically they're often slow to speed them up significantly. But I know that the templating basically works by, let me pick what I already know how the assembler code for this instruction, for this bytecode instruction should look like. So there's basically no room to make this any kind of smarter or faster up front, and saying, hey, C2 maybe, or C1, which I think maybe contributes to 50% of the performance at least before C2 kicks in. So there is really, that's end of line, end of story, basically.
Yes and no. The reason I say that is because there is another thing that we do at Azul with our prime JVM, which used to be called Zing, and that's called Ready Now. And what Ready Now does is to say, okay, let your application warm up, and then we take a snapshot of the running application from the point of view of recording all the classes that are loaded, all the classes that are initialized, all the profiling data that was collected for the C2 compiler. And we also take a copy of all of the compiled code. So when you restart the application from that again, what we can do is we can immediately load classes and initialize classes that we need, and we can potentially reuse compiled code straight away. So we can do a lot in that sense. With Ready Now, but it's still not quite what I'm going to talk about here. So bear with me, and we'll come back to that at the end, and if you've got further questions. Okay, so one of the things that people often say in terms of how to improve the performance of this is, well, why not use static compilation? That's what C and C++ use, and you get immediate running your application with compiled code. It's all heavily optimized and so on. Isn't that the answer? Because it works for C, it works for C++. Why don't we just use that for Java? And obviously that has benefits because you don't end up doing any interpreting. So you avoid the problem of slow code to start with. You don't have to analyze the hotspots. You don't have to compile code whilst the application is running, because again, that's taking resources away from your application. Let's say you're running in a 2 vCore container. If you're starting to compile code on 1 vCore, that literally halves the amount of processing power you've got to run the application itself. So it's not just you're running slow code, you're also running on less cores than you would if you're not doing compilation. So ahead of time compilation sounds good. You start at full speed straight away. So everything from an ahead of time compilation perspective sounds ideal. Now, if you look at GraalVM, that's something that's become very sort of interesting and very popular fairly recently. And that takes that idea. Ahead of time compilation generate what they call a native image. Now, a native image is compiled for a specific platform. So it's Windows with Intel. You lose the write once run anywhere, but a lot of people say, well, I know I'm going to deploy onto Linux running on Intel, so I'll just compile for that. So we've solved the problem. That's the end of the presentation. Just use GraalVM. No, that's not the end of the presentation, because there are other things to consider. Not so fast. And I mean that in 2 different ways. So the problem with ahead of time compilation is that by definition, it is static, meaning that you do all the compilation before you start running your application. So what does that mean? Well, it means that the compiler actually has no knowledge of what the code will do when it's running. And there is a technique that you can use to sort of get around this partially. It's called profile guided optimization. It's been around really since the beginning of compilation itself. The idea behind profile guided optimization is that you use static compiler, you compile your code and then you run it, but you also profile it at the same time. You run with a representative workload. You could do it in production if you want to, and you see how the code is actually being used. Collect all that profiling information, and then you feed that back into the compiler, recompile again statically with the profile guided optimizations, and then get better performing code. So that does improve performance, but it doesn't address all the things, as we'll see as we go through. Now, I mentioned speculative optimizations, and these are very, very important to the idea of how we can deliver better performance with the JVM using JIT compilation. Now, I'll give you a couple examples of what speculative optimizations are. Let's say we have a simple data class, called it animal, and it has some state, which is its color. Great. So we'll make that an encapsulated value, and then we'll provide an accessor method, getColor, which returns the color. If I use an instance of an animal in my code and I want to get the color, I call the getColor method. Now, technically, the way that that gets compiled is the compiler says, right, so you're going to call the getColor method on this object. So we create a stack frame, we call the method getColor. getColor will then return the color of the animal. We pop the stack frame off, we get the result. So that's pushing a stack frame on, popping a stack frame off, which is very inefficient because all we're doing is returning the value of the color. What the compiler will do is it will say, well, I can simplify things because I'm compiling the code, I have complete control. So long as I respect all of the requirements of encapsulation, meaning that people can't change things directly, then I can change that to make the color reference appear as if it's public. So I don't need to create a stack frame. I then don't need to pop the stack frame off. I simply reference the value of the animal, and I can then get that value and make it simple. That's really good. But the problem is that because Java is a dynamic language, not dynamically typed, but it is dynamic from the point of view of class loading. We can load classes at runtime, which means that we might have a different implementation of animal, and we might have a different implementation of the getColor method. So our way of optimizing, where we know that that getColor method is only going to return the value of color, only works if we can guarantee that there's one implementation of that getColor method. And if something changes at runtime by class loading, then that invalidates that optimization and we can't use it. So that limits what we can do in terms of static compilation, but not with JIT compilation, because of course the JIT compiler can look at things and know, right, if we load a new class, it changes the way that thing works, then we have to recompile the code accordingly. Give you a second example, which is a little bit more complicated, but shows some of the real power of what we can do with speculative optimizations. This uses a technique called branch analysis. In this method, I have compute magnitude, which takes a value. And then the first thing I do is I test to see whether the value is greater than 9. If it is, I need to call a different method, compute bias, with the value to calculate what my bias is going to be. If the value is not greater than 9, then I simply set the bias to be 1, and then I return the log base 10 of bias plus 99. Branch analysis says we profile the code as we're running it. So this is the C1 generated code with profiling information, and we will count how many times we go through each branch of that if statement. So how many times we go through true, how many times we go through false. If we find when we come to compile that code with C2 that we have never been through the true branch, then the compiler can speculate that in the future we will continue to never go through the true branch because that's the way the code is working in this case. Based on that, the compiler can then can design that code in a better way to allow us to optimize. So what we can end up with is a situation like this. So still got our compute magnitude method, takes the value. We still have to have a test on value to see if it's greater than 9, because we have a contract between us, the developer, and the compiler, and it has to respect that contract in terms of doing what we want it to do. Even though it's assuming that we won't have a value greater than 9, we must be able to deal with a value that is greater than 9. If the value is greater than 9, then we call uncommon trap. Uncommon trap says that the thing that we speculated about, our assumption has turned out to be wrong, and therefore we must throw away that code because now it's invalid and recompile it based on the original code that we had. So that's a de-optimization, and we don't like those. However, if we don't get a value that's greater than 9, because we know that we've set the bias to be 1, and 1 plus 99 is 100, and the log base 10 of 100 is 2, then we can avoid all of that work every time we go through the method and simply return the value 2. And that makes our code much simpler, much faster. Now, I say it's a slightly contrived example, but it demonstrates what we can do in many different ways. And the cleverer the compiler, the more of these types of things that we can do. So with that, we can much more heavily optimize our code. What we found in terms of Azul's work is that over 50% of the performance gains we get with our JIT compiler are due to speculative optimization. So it is a very powerful way of improving the way that the code works running on top of the JVM. It only works if you can de-optimize. If you try and do that with a static compiler, then you have a problem because you can't throw away that code and recompile at runtime, because remember, you've compiled everything ahead of time. What you can do to get around that is to have multiple paths that you can select from in terms of your code. So you'd have one set of code compiled for the whole method, then you have a set of code compiled for one speculation. You could have another set of code for a different speculation. But that becomes very complicated and leads to a lot of bloat in terms of the compiled code that you generate. So that's a very, people don't use that technique very much. De-optimizations, as I said, are what we try to avoid because they're very bad for performance. We've wasted time compiling code. The assumptions turned out to be wrong, so we have to throw that code away and then recompile it. So now we're compiling the same method at least twice, and that is very inefficient. So we don't want to do that. It's wasting CPU cycles. So if we just sort of do a comparison between AOT and JIT and look at the pros and cons of both. AOT has the idea that you can not have as aggressive method inlining because we don't know about class loading at runtime. That's one of those important things because method inlining is a very common technique for improving things. If you can't guarantee that the method is going to be the one that you know, then you can't inline it because it could change at runtime. You're limited with ahead of time compilation. You can't do runtime bytecode generation. A lot of frameworks, things like Spring and so on, they tend to do bytecode generation at runtime. Reflection is complicated. If you've tried using GraalVM, then you will know that in terms of using reflection in your application, it is possible, but you have to declare all of it up front and it has to all be compiled in. So it makes it a lot more complicated in terms of how you use that. Speculative optimizations can't be used unless you use that sort of multi-path idea, which again gets very complicated and makes the code a lot bigger. And overall, typically, I'm not saying in every case, overall, typically you will get lower performance than you will with JIT compilation. The pros are obviously that you get full speed from the start because you're immediately starting with your fully compiled code and you don't have that overhead on your CPU of having to compile code as well as running your application. On the JIT side of things, it's pretty much the opposite. So you can use aggressive method inlining because you know exactly which method is loaded at any one time when you're doing the compilation. If that changes, you can invalidate the code and then recompile it. You can use runtime bytecode generation because you're using a JVM, so it's using bytecodes. Reflection is, and I'll say, relatively simple. I don't think anybody's ever going to claim reflection is simple. You can use speculative optimizations, and typically your performance will be higher. However, as I've said, the downside is it requires warmup, and you've got the overhead on the CPU to compile the code at runtime. So if we go back to our performance graph and we look at what we get with JIT compiled code, if we compare that to ahead of time compiled code, we're going to see a profile like this. Instant startup, run at maximum level of performance all the way through. So that's really good. But we can see that the overall level of performance is lower than we get with JIT compiled code. Even if we factor in profile guided optimizations to try and improve things that way, you're still never going to get that same level of performance because you can't use the same number of speculative optimizations, you can't do the same method inlining and so on. So we're restricted in terms of what we can do for optimizations. So what about a different approach? And this is where we come to the whole idea of this Java on CRaC. Now, if you look at Linux, there is a piece of technology that's been around for a while now, and it's called Coordinated Resume in User Space, or CRaU, as people try to pronounce it as a word. The idea of this is to take a running application and to be able to freeze it at a given point, store that state in user space, so that's the important thing, in user space, and then be able to restart from that given point at some later time. Now, if you think about the way that Linux works, Linux is a time-sharing operating system. And again, if you go back in time a little bit and you look at when machines only have one processor and one core, the way that we would make people think that they could run many applications at the same time was by sharing the processor. What you would do is you would start your application, the application would get a slice of time to run on the CPU, and when it got to the end of that slice of time, it would get context switched out. So the operating system said, right, you've had enough time, we'll take a copy of all the state of this, so your registers, your program counter, everything that relates to the state of that application, and we'll shift that context into memory so it's ready to go again at some point later. And then we'll take the context of another application and move that back in and run that application for a little bit of time, and then we can swap between the two. So the theory is quite straightforward, because the operating system already does all of this thing, as it runs multiple applications. What CRaU does is take that a step further by saying, rather than having the context stored directly in memory or maybe written out to disk in terms of the swap area for the operating system, what we'll do is we'll write it out to user space and keep it in a set of files so that they can be reused at a later time. Potentially, you can take those files and move it to a different machine. Now, as long as the architecture of the machine is sufficiently similar, then you won't have a problem. But obviously, if you've got a different machine with a different architecture, it's very difficult to try and move a running application to that different machine. So we end up with a set of files, and we can then move those or restart them where we want to. Now, the way this works is mostly it's implemented in user space. There is a little bit of stuff that goes into the kernel that's been around, like I say, for quite a long time now. It's since 3.11. And the reason that this was developed was really looking at the way containers worked. What they wanted to be able to do was migrate containers for microservices between different machines and also start up multiple instances potentially. The set of features it supports is really quite impressive. So you can take all the information about your process, your threads within that process, any memory that's being used, the state of that gets stored. Even things like memory map files and shared memory will be replicated in terms of the state. Open files, pipes, FIFOs, sockets, all of those things, even inter-process communications channels can all be frozen in this information, right down to timers and signals. And they even found a way of being able to rebuild a TCP connection without having to do negotiation. You could literally rebuild it from one side only. So the challenges with CRaU are that if we take our state and we move it to another machine, as I said, if you've got a different architecture, that's one big problem. But there are other problems. If you take all of that state that I just explained and you say, well, open files. Well, what happens if the file doesn't exist on the machine that you're moving it to? Suddenly you're trying to run an application that has an open, /tump/foo, and there is no /tump/foo on the machine you've got it on. Or what happens if that file is different between the two machines? So you have you're reading from a file, you get to a certain marker, and then you move it to a different machine. And this can also affect what happens if you let the application sit for a while and then you restart it. The file could have disappeared, the file could have changed. It makes life very, very complicated. So the other thing that you're limited is you can't restart multiple instances of this. It's a one-shot thing. So the idea is that you've got one process, you restart that process, not multiple times. When we looked at this, we thought, well, this is pretty interesting. How about if we applied it to the JVM? JVM is just an application running in user space on top of the kernel. So why don't we treat that as something that we can use with CRaC and freeze a running JVM and then restart it at some point later. And yes, you can do it, but it's not the best way of doing it. So what we came up with was what we call CRaC, and CRaC stands for Coordinated Restore at Checkpoint. And the really important thing here is the coordinated aspect of that. What we decided was we would make the application aware that it was about to be checkpointed, meaning that we were about to freeze its state in a set of files. And then when we restarted it, we would make the application aware that it was being restored. So what we can see here is we've got an application that's running, and at some point we decide we're going to do a checkpoint. So then the application is notified that a checkpoint is about to occur. So it can then do certain things in order to tidy up before the checkpoint occurs. We can then take our checkpoint, store those files, and at some later point, restart our application, but again, send a signal to the application, say, you have just woken up from a checkpoint. There may be things you need to do to make things work in the way that you want them to do that safely. And what we also decided is we would enforce more restrictions on an application than you get with CRaC. In this case, what we said was no open files, no open sockets. That just makes life a whole lot easier. But because the idea is it's coordinated, when we send a message to the application that a checkpoint is about to occur, the application can say, right, let's close the files that we're using. When it gets a notification that's being restored, it can go, okay, let's open the files that we were using before, potentially, doing we can do checksums on them to see if they've changed, take certain application based on that. So there's a much more flexibility in terms of how you can restart from a checkpoint and do it in a safe way. The way this works is through a simple API. It really is a nice, simple API. So the first thing we have is the concept of a resource. And we've defined that as an interface which has two methods. The, again, very originally named before checkpoint and after restore. No prizes for guessing which each method does. So the idea here is that if you look at your application code, you look at the classes you've got and you figure out which of those classes need to be made aware that a checkpoint is about to happen or a restore has just occurred. And that way you can mark those as being resources, you implement the interface, and you implement those two methods so that before checkpoint, let's say you've got an open file, you can put the closed file in that before checkpoint. When you restore, you get called the after restore, you can then open that file, have a valid file descriptor so that your code then can continue using a valid file descriptor to a file, which could potentially be on a different machine, remember. So it makes things a lot easier from that point of view. So you look at all that, figure out what needs to be done. Then what we need to do is we need to tell the JVM about those resources. We do that using a context, and a context has a method register. So we register our resources so that the JVM knows to call those methods on those resources as it's doing the checkpoint and as it's doing the restore. In terms of how we get the context, you can create your own if you really want to, but there is a global context that you can get through a static method on the core class, which is part of the API. So it's very straightforward. What you do is you simply say, I've got a set of classes which implement the resource interface. For each of those, I will call the register method on my context, which I will get from the global context from the core. Now, the way this works is that the context maintains a list of the resource objects. When the before checkpoint needs to be called, the order of that list is important. What it will do is it will call the before checkpoint of the classes that are in that list in the sequence that they are registered. So you as a developer can decide which order you want them to be in. Let's say you've got 3 resources, 1, 2, 3, and the order is important to you, so you register them as 1, 3, 2. Great. So the before checkpoint method will be called in the order 1, 3, 2. When you get to the restore, the after restore method will be called in the reverse order. So it'll be 3, 1, 132, because is that right? Yeah, I think that's right. 132, 231. Yeah, 231. Anyway, so it'd be called in the reverse order. The reason being that obviously if you've got certain things that need to happen in a specific order as you're going through into doing the checkpoint, then you want that to be in the reverse order so that you can undo things. It's like going down the stack and then coming back out the other way. So the order is important, and you can have predictability there so that you can do it in the right way for your application. So as an example, let's say we have a simple Jetty server. So we create a server manager class with a server instance, and our constructor will create a server on port 8080 with a handler, and we start the server running. Great, so we've got that running. What we can do is, having run our application, we can decide to create a checkpoint. And the way we do that is using jcommand. We've included a new jcommand that we can use to do this. So the way it works is you do jcommand on the application that's running, and you just say jdk.checkpoint. That will then initiate the checkpoint. JVM will call the before checkpoint methods on things that have been registered and generate external files. What you will then see is this message here, which says command executed successfully. That is the one thing that we really, really must change, because that is wrong. It did not execute successfully. Because if you look at the log file, what you'll see is that it actually threw an exception. The reason it threw an exception is because there is an open socket. We have a server running, and we didn't do anything to stop that server running. So the JVM will look at that and go, no, we don't support open sockets in terms of a checkpoint, so we can't do that. If we want to change the code, then what we do is we take our server manager, we implement resource with that, and then in the constructor, we will register this as a resource with the global context that we get from core. We implement the two methods, before checkpoint and after restore, and very simply, all we have to do in before checkpoint is stop the server, and then when we come back again, we start the server again. We can, if we want to, not do the checkpoint externally, we can do it internally in our code. So there's another method on core, which is checkpoint restore, and that will generate a checkpoint. So the way that this works is that you put that in your code, and you know that when you go into that method, that's where the checkpoint will be made. So the files will be written out, everything will happen in terms of all the resources and so on. When you return from this method, that's when the restore has happened. So you know that when you go in, you do a checkpoint, some point later, maybe on a different machine, you come back and you've just done a restore. Potentially, it could throw either a checkpoint exception or a restore exception. How good is this? Does it actually work? Well, what we've done is to create a proof of concept. So we took Linux, we took the JDK running on Linux, we used OpenJDK, obviously, and we used CRaC as our way of implementing the CRaC from the JVM. One very important thing to say is that the CRaC is not tied to CRaC. So CRaC is a way of doing a checkpoint restore at the operating system level, but the API and the way this is implemented in the JVM doesn't rely on that. So if we can find different ways of doing it, then we can use those. So here are some example results that we got. So we ran some sort of fairly typical workloads and applications, and we wrote a simple Spring Boot application. We had a Micronaut application, Quarkus application, so on. And what we did, we timed how long it would take to get to the first operation for that application. And when we did Spring Boot, it took about 4 seconds to get from starting the JVM all the way through everything and getting the Spring Boot application actually processing data from our users. Using CRaC, that dropped to 38 milliseconds. So that's 2 orders of magnitude faster, which is a pretty impressive result. Plus, of course, you get, assuming that you can like run it for long enough before you take the snapshot, then you will get all of the benefits of that compiled code. Same thing with Micronaut, that took 1 second to come to first operation, and that dropped to 46 milliseconds with CRaC. Quarkus, which sells itself as being fast startup and super fast Java startup, that took a little bit under a second and dropped to 33 milliseconds using CRaC. And XML transform, which is probably not the best example, but again, that was 4.5 bit seconds, dropped to 53 milliseconds. The other thing that we can see is that by avoiding that warm-up time, we can improve throughput and the ability to handle transactions. So here what we're doing is plotting how many transactions, how many requests we can handle in a given space of time. Because we don't have to go through the warm-up, obviously that shifts the graph down, and we can see in the case of Spring Boot, we could get through, you know, a higher number of or the same number of transactions in a lower time. So throughput effectively is improved at startup. Same thing with Quarkus. You can see a slight difference in terms of the spread between the two lines. So just to show that it took longer for Quarkus to warm up. To summarize then, basically, we've got some ideas for how to take this further. So future directions. One of the things is to make the JVM itself more aware of the fact that a snapshot is going to occur. One of the things you have to think about is that in order to record all of the state, we have to take a copy of the heap. And if you're using a big heap, that results in big files. So if you've got an 8 GB heap, you get an 8 GB file for your heap, or 16 GB file for a 16 GB heap, and so on. What we could do potentially is say to the JVM, right, if we're going to do a checkpoint, let's have the JVM do a full compacting GC on the heap. So we compress everything down to the bottom of the heap, eliminate fragmentation, and that way we could reduce the size potentially of the heap image. Because, you know, if you're not using 100% of your heap, then if you're only using 25% of it, then you get a 2 gig file rather than 8 gig file for that size heap. We could also potentially compress that, so we could use compression algorithms, you know, zip it, that type of thing. But of course, the sort of what you have to weigh up is the benefit of the compression in terms of the size of the files versus how long it takes to uncompress them. So that would delay the amount of would delay startup, so you wouldn't get as big a benefit from that. The other thing we're looking at is supporting other mechanisms to do the actual snapshot for the JVM. I said that CRaC is one way of doing it. We're looking at other things that potentially we could use. Docker supports a way of doing snapshots, which actually uses CRaC underneath. So that's, you know, really still using CRaC. And we're looking to see if there's a way of doing it on Windows, potentially on Mac as well, because, you know, if we're going to get it into OpenJDK and make it part of Java, then it needs to be cross-platform. Just summary then, CRaC is a way to pause a JVM-based application. So you can do a checkpoint and then you can do a restore, potentially multiple times. That could work very well if you do put the CRaC files, or the CRaC files into a Docker container, because then even though they could be running potentially on the same hardware, you've got isolation, which means that you can use the same set of files multiple times. That's not a problem. Potentially very fast, extremely fast startup for our applications, and with all the benefits of JIT compilation from that point of view of speculative optimizations and so on, but without the overhead of having to go through the warm-up process as you do it. It is now an OpenJDK project. We submitted this as an idea to OpenJDK, and the people on the OpenJDK said, yep, looks interesting, we'll actually create a project. Go to OpenJDK. As you can see, there's a couple of links here to the wiki for OpenJDK java.net, and also our GitHub repo, which has the example of the applications plus the proof of concept JDK that we built. So you can download JDK 17 and try it yourself. Just briefly mention what we do at Azul in terms of Java. We have two things that we do, both of which are Java. So there's Azul Platform Core, which are our builds of OpenJDK, similar to Amazon Corretto, well, identical to Amazon Corretto, or Red Hat Linux, JVM, JDK, and so on. We support all sorts of different versions, going all the way back to JDK 6 if you want, both commercial and free versions of that. Platform Prime is the other side of our business, which is this, what used to be called Zing. So we do things like replacing the garbage collectors with a truly pauseless, fully concurrent collector. We also have a replacement for the C2 JIT compiler called Falcon, based on LLVM. And as I mentioned, ready now, so that we can do things like that. Nice thing that we're working on at the moment with that is the idea of the cloud native compiler, JIT as a service. So extracting the JIT out of each JVM and then sharing it as a centralized service, so you don't have the overhead on each JVM. Free offer. if you're interested in more presentations like this, we're very happy to do this, not just for JUGs, but if you have a group of developers in your company, then we're happy to do presentations on this subject or other subjects that might interest you, like what's new in JDK 17 or what we can do with Zing in terms of performance, things like that. So these are sort of things where people do brown bags, you know, lunchtime, lunch and learn type of things. So if you're interested in that, feel free to reach out to me either through my Twitter handle, or you can reach me at my email address here. One last thing I will do, I will show a demonstration of this actually working. So what I need to do is go back and share a different part of my screen, if I can find it. Yeah, where's my VirtualBox gone? Hang on. So I'm just trying to find the right, there we go. Let's try that. Right, sorry, can you see a terminal at the moment?
No, just the.
No.
Okay, let me. Gone. Right. Okay. Yeah, let's do that later. Okay, so what I've got here is a very simple application. And what it does is essentially to kind of give some idea. We just wrote a simple application that has a million element array, which is treated as a cache. And the cache is filled with prime numbers, which are calculated by the application. So it's just a something that produces a workload. And the idea is that the elements in the cache will time out over time and get refilled. And so if I run the application, so let me just sorry. Right. So the start. Let me just see if I can. Oh, well, yeah, there we go. Right. So essentially what the start script is going to do is just run Java with a checkpoint pointing to a set of a directory where it's going to store the files, and it's going to run the application. So if I run this, what will happen is it will start calculating and filling the cache.
Hey, Simon, you're no longer
Yep.
sharing your screen.
Oh, am I not?
It's up.
Okay.
Yeah, that way.
This is annoying. Hang on. How's that?
Yes.
Can you see it?
Yes.
Okay, good. Right. So on the left-hand side there, you'll see I'm running the application, and the time it takes to calculate each sort of cycle, you can see it's dropped down from about 8 seconds, and it's currently running at 31 milliseconds. Now, if I, on the right-hand side here, what I'll do is I'll create a checkpoint. Oh. Right. So that's created a checkpoint of that application. And what I can now do is I can come over here and using the files that have been generated, I can start it again. So again, if I look at restore.shell, all that's going to do is just going to do Java with where to restore the CRaC from and the CRaC files. So I don't even have to worry about giving it the details of the application because it knows exactly what the application is. So if I run that, what we'll see is now we're running on run 18 and we're immediately running 31 milliseconds. So if I go back, obviously we've got to run 17 here, and then we've started up from run 18, and it only takes 31 milliseconds straight away. So we're immediately running where we want to. Now, what I can do is I can actually terminate that myself. If I wanted to, I could use the same set of files again, and we'll start off from exactly the same point. So we're back to run 18. So the state is identical to what we had before. One thing that we did find that was interesting with that was when we first wrote this application, because the cache drops things out over time. Let me just stop sharing my screen there. Yeah, because the application dropped things out over time. When we wrote the application first and we did our first snapshot and restore, the first restore went right back to the beginning and started filling the whole cache, and we couldn't work out what was going on. Then we realized it was the fact that because the time on the system clock had moved forward by such a significant time, the cache had just completely emptied itself. So this is one of those things where we had to do the before checkpoint to store the current system time. And then when we came into the after restore, we did a delta between the current system clock and where we did the snapshot. And then we could apply that so that we didn't drop everything out of the cache straight away. And that way we could pick up. But that was a good learning curve for us. So that is Java on CRaC. If anybody has any other questions, I'm happy to take those. Silence. Yeah, I mean, like I say, it's all free. It's on OpenJDK. The GitHub repo and everything is available. So if anybody's interested in looking at this in a bit more detail, then I would certainly recommend doing that. Yeah, so I hope that's been interesting.
I'm gonna go ahead and stop the recording.
Okay.
Since there wasn't really any questions.